The technology wouldn't work. Sorry about that. So last class, after we did all the first day stuff, we started talking about what types of tests we did first semester, and then we finally started discussing ANOVA. So remember, ANOVA stands for analysis of variance, but it is a test that's comparing means. The reason why it's called analysis of variance is because you want to see how they vary from one another, okay? So the numerator is called the variable between the sample means, okay? So that's the variance between. So that's comparing the means to one another. And then the denominator is called the variability within. So how spread out is each sample, and then you compare that to one another, okay? And then we had different scenarios. This top one, all of them were within that population, right? They're all pretty similar, so we would probably get failed to reject the null. This one, they're more spread out. This one doesn't even look like it's from the original population because it's so far away, right? And then the means are really far away from that population mean and that first sample mean. And so again, we would probably get reject, that they're not equal, okay? We talked about why can't we run multiple t-tests, and the reason was it increases your probability for a type 1 error. Yep, good. So the next thing we were going to discuss was the F test statistic, okay? So this box right here is actually showing, the box is showing what the test statistic is. So all of this right here above this line is your numerator. So that is your variability between the means or among the means, okay? So you're going to compare them to one another and then get a single data value, all right? Then these down here, that's called the variability within. So that's comparing the variances. That is our denominator. So what happens if you get a large numerator? So you get a ratio that is larger than 1. That means at least, I cannot spell this morning. Oh, great. Already lost it all. At least one of the X bars is really far from mu or the others, okay? So if this happens, just remember, big difference, okay? If there's a big difference, then you're going to get a big test statistic and you're going to reject the null, okay? So when the numerator, the means are drastically different, you're getting a larger numerator, which is going to give you a number bigger than 1 because it's bigger in the top, okay? So if there's a big difference in your means, then you're going to reject, okay? So if this is a big number, if F is a big number, that's because there's a big difference between your means, which means we're going to reject, okay? That's just a way to try to help you remember. So if there's similar variability, you're going to get a smaller test statistic and you're going to fail to reject the null. Okay? Same thing with if you get a small numerator, that means the means are all really close together, all right? Then they're all really close to each other. Let me write that. All really close to one another. Then you're going to get a small number. There's not a big difference. It's a small difference. So this is another scenario where you would fail to reject the null. Okay? So I had written it and I deleted it, but this is your numerator. Your numerator is comparing the means to one another. It's called the variability between, and then this is your denominator. It's called the variability within. All right? So you'll notice on this one, it does say calculator. So your calculator will run a one-way ANOVA, which is also called a single factor, okay? So your calculator will run a one-way ANOVA test. It will not run a two-way ANOVA test. So I will show you with Excel. That's why I went through all that hassle at the beginning of the block trying to get it through Zoom and sharing the computer because I wanted you to see it in Excel, okay? So one-way ANOVA, which is also called single-factor ANOVA, if you read that in your literature, okay, you can use your calculator. So 21 students at the Autonomous University of Madrid in Spain were selected for an informal study about student study skills. So we have 7 first-year students, 7 second-year students, and 7 third-year students. They're all undergraduates, and they were randomly selected, okay? The students were given a study skills assessment having a maximum score of 100. As researchers, we are interested in whether or not a difference exists somewhere between the 3 different year levels. Okay, so they were given a study skills assessment. So if you look, here are my year 1 scores, okay, year 2 scores, year 3 scores. These are different students, and they're all independent of one another, randomly selected, okay? So your year 1 average score for the readiness is a 71.71. Everybody see that right there? Your year 2 students have an average score of 75.29, and your year 3 students have an average score of 76.57. Would you say those are all relatively close? Yeah, they all seem pretty close. And then if you look, the overall mean, which is X bar with another bar over it, or you could have said from the population, so mu, would be a 74.52. So all of those are relatively close to that as well. All right, then you have S. S is what? Standard deviation for each sample. That's what S stands for. Good. So you'll see 13.16, 11.19, and 13.05. So again, those standard deviations are also close. Okay? So these seem pretty close to one another. So if they seem pretty close to each other, do you think the averages are going to be equal, or do you think there will be a statistical significance in the differences, which would be our alternate, that they're not equal? Equal, yeah. 71.7, 75.2, 76.6. They're all pretty close, so I don't think I'm going to get to reject, right? So that's what we do first, okay? And I'm going to write over here so I have plenty of room. Write small, okay? Don't write ginormous or it's not going to fit, okay? All right. So H sub O would be my average for the first year students is equal to the average of the second year students is equal to the average of the third year students. If I had more groups, I would just keep going, okay? The alternate is that at least one of the group averages is different. But usually, if we're using the math symbols in the first one, we're going to use the math symbols in the second one. But the other day I told you, when you run this test, you're showing that at least one of them is different from the others. Now, you could get the 2 of them are different, but at least one is. 2, 3, 4, whatever, okay? So my alternate is going to be that mu sub 1 does not equal mu sub 2, does not equal mu sub 3. The next thing we always do is check the conditions, okay? So if you are doing this for your SRP, or for your final project in here, remember, I'm going to let you choose a topic and collect your own data. You have to check the first 3 conditions for each group. And then the 4th condition, you just check it one time, okay? So the reason why I reviewed with you the other day is because it's really important to remember t-test, 1 prop z-test, 2 prop z-test, all those tests we ran first semester, right? Well, we're looking at averages. What were your conditions when we had a test for averages, or an average compared to a claim? What were your conditions? Do you remember for a t-test?
Random.
Yep. Same thing for this one. Random. Normal. And the third? Independence. So I'm not going to make you check it because these tests are kind of tedious and time consuming. So I'm not actually going to make you check it. I do want you to write them each time, okay? But I'm not going to make you actually check it. If you do this, though, for an SRP, you do have to check those 3 for each group. And then if you do it for my final project, you also have to check it, okay? So these three are exactly like when you were checking averages first semester, okay? You do have a fourth one, though, and the fourth one is that the variances are similar, okay? So if you look, I will answer that one. I'm going to say yes, since the standard deviations are close. Okay? Now, there's no magic number that I can give you that says if they're within 2 standard deviations of each other, or if they're within 3 or 4 or 5. I'm sorry. That's part of why it drives me a little bit bananas, because I can't give you like a concrete number, okay? So, when you're looking, as long as they're relatively close to one another, 13, 11, 13. Those are close. I don't have one that's like 100 or 37. You know, if that happens, I would say I don't think that one is similar, so I'd probably want to collect another sample. I feel like maybe there was an error or something, okay? Otherwise, if they're pretty close to each other, I would move on, okay? All right. And sorry, I can't give you a number. I've never found one. All right, so now we're going to use our calculator for this first one, okay? So if I give you a quiz or a test and it's one-way ANOVA, you can complete it in your calculator, okay? If it's two-way ANOVA, you'll see later in the notes in the next couple sections, I will give you the Excel report out from it so that you don't have to try to have a computer and all that stuff for a quiz or a test, okay? So get your calculator. And we're going to go to Stat, we're going to go to Edit, and we're going to put our data in our list. So you can see here, in List 1, I have my first group of student scores. So I have 82, 93, 61, 74, 69, 70, 53. Okay? For List 2, I'm going to put the year 2 scores. So 71, 62, 85, 94, 78, 66, and 71. And then the year 3 scores, 64, 73, 87, 91, 56, 78, and 87. So if I had just given you raw data without those means and standard deviations, you could use your calculator to find it. So I'm going to review that with you really quickly from first semester, okay? I'm going to go to second mode, which quits, then stat, arrow over to calculate, one variable statistics, and I'm going to do that for list 1. And you can see right here, it gives me my X bar. I went up too much. Aw, man. Okay, well, if you did it right up there above that S sub X, you would see the X bar. Sorry. But then you see S sub X is my sample standard deviation, which is 13.16. And that's what I typed. Okay? So stat, calc, 1 var stats, and I can change that L1. Oh, I'm struggling today, y'all. Try again. I'm going to make that second 2, which is L2. Hit enter, and you can see right there, X bar 75.285, which I put 75.29, and then S sub X is 11.19. Everybody see that? Okay, so that's how you can get your mean and standard deviation. You just go to stat, arrow over to calc, and do one variable statistics, and change it from L1 to L2, L3, whatever. Okay? All right, second mode. And what do we normally do for these? How do you normally run a test? You go to what button? Stat. You arrow over to test. And this is a what? ANOVA, okay? Which is all the way down here. It's H. Yep. Now, the difference is usually when you choose a test, it goes to a new screen that then you just tell it's in L1 or it's in L2, or I can put in X bar, I can put in S, or I can put in how many out of a proportion, right? So X and then N. But on this one, when you do it, it puts it on the home screen, and it's waiting for you to tell it the command, okay? So where did we put our data? L1, L2, L3. So I'm going to hit second one and tell it L1. And then you have to put a comma between it. So the comma is above the 7. Press the comma. And then second 2, which is L2, comma. And then second 3. Now, if I had more groups, I would just keep separating them with commas. Okay? Make sure you put the comma. If you don't, it's going to give you an error message. You have to put the commas. All right? Then you press enter. And you'll see it gives you lots of information right here. So it gives you F and P. That's what we're going to pull from this. Okay? Everybody have it? Okay. So on my note sheet, when I'm writing this, I always ask you to tell me what kind of test are you running, what is the test statistic, interpret it, what is the p-value, interpret it, and then give me your final results. Okay? So this is a one-way ANOVA. And I put my data in the lists, okay? So then I went to stat, arrowed over to test, and I chose option H, which was ANOVA, and then I put L1, comma, L2, comma, L3. So you do have to put that, which is above the 7 key, okay? You don't have to write that every time. I'm just writing it so that if you look back at your notes and go, what? Where was that comma? You'll have it, okay? Remember, write small. We have a lot to interpret. Okay, so now we're going to pull our F statistic, okay? So F equals, it was about 0.2837. Okay, remember at the top of this page, I said if it's a big number, there's a big difference in the means. Is that ratio bigger than 1? No. And we didn't think it was going to be, did we? We said all these means are pretty close together. So this is a small number, okay? So this small test statistic indicates that the variance between groups is small compared to the variance within. Okay, and remember, the variance between is comparing the means to one another, okay? The variance within is comparing the variability of each sample to each other, so that's the standard deviation, okay? Let me write it. You would not write this if you were interpreting, but I'm just going to say it one more time. Remember, this is the numerator. This is comparing each of the X bars to one another, okay? That's what that is. And then the variance within, that's comparing the S's to one another, the standard deviations, okay? You don't have to write that. I just want to explain. And again, that reiterates why we call this analysis of variance, because we're looking at how they vary from one another, okay? All right, one more piece, because if I were sitting in the audience and you said that to me, I would understand you, but I might sit there and be like, so what does that mean, right? What does that tell me? So I also put, this small value suggests that the averages for each year are similar and the differences are likely due to random chance. Okay? Okay. Any questions on that? How to interpret the test statistic? No? So now let's interpret our p-value, which y'all have been doing that since first semester. That's the same. And the test statistic you've been interpreting, but each one is different, right? What it's indicating. So the p-value, might try to fit it right here. The p-value was what? Look at your calculator. 0.756. That's a pretty big p-value, right? So if the null is true, if the averages are equal, that's my null. So if the averages are equal, then there is a 75.6% chance that I found that at least one average is different. And that's the alternate, okay? Okay, so now last step is what you've been doing forever. Compare the p to alpha, right? So the p-value was what? Thank you, 0.756. We're going to compare that to our alpha, which for ANOVA test we use 0.05 typically, okay? So 0.05, so the p is high, so we let it fly. Fail to reject the null, which is what we thought was going to happen, right? So when I tell you when you're doing a project to first analyze the data, just look at the descriptive statistics, that's what we were doing right here. We said they all seem pretty close. So I don't think one of them is going to be different. At least one of them is going to be different. I think they're all pretty close, so I'm probably going to fail to reject, okay? And that's okay. You start to form an idea about your data. Then you actually run the test to see if it's significant or not, okay? All right, so we failed to reject the null, which means there is or is not. There is not. Good. There is not sufficient evidence at the 0.05 level of significance to conclude that there is a difference in average scores for students. Okay? And you don't have to write this, but if you go back to that graphic I gave you, this one, this situation, this situation looks like the first picture. Okay? So if you're a visual learner, that would be this situation up here, where they're all kind of within, yes, they're different, but they're pretty close to that population mean and one another, right? So it would look like that first picture. Whereas when we reject, it's situations like this down here. Okay? Need me to go back?
Yes, please.
Okay. Okay. You do not have to write that second piece with in the purple. You don't have to write that. Oh my goodness, you have all kinds of extra space. You wrote tiny.
You said write small.
I did write small. You wrote tiny. That's
This is
impressive.
small for me.
You wrote microscopic.
This is
Right, you
small
need
for
a
me.
magnifying glass to be able to read that.
Well, in the past, I've written like smaller, and it's been too big.
I know. I remember.
And I have to get sticky notes and take them on there. So I
Yes.
was like, I'm gonna write small because she said write small. This is small.
See, I just wrote and prayed.
Wrote and prayed. Please let it fit.
Yours is small.
Yeah, you did good. Everybody,
No, but
were you able to
last
fit
time,
it?
you remember when
Look
I
at
did,
y'all.
Like 5 different sticky
Yes,
notes
good
on
job.
it?
I
You didn't have
know.
it there.
Ours is basically the same size.
Um,
No, it's not.
Yes, it is.
Miss Harold, this is not the same
Yes.
size.
Are they not like the same size handwriting?
They're both small. You did great. Were you able to fit it all?
See, she's
See,
not
everybody.
gonna-
I'm not lying.
Right,
Stop it.
But she's not going to just come out and say, yours is really small.
No, I think you all did great. So sadly, I thought I was going to use my MacBook, right?
Oh, no, you're
So
not
I
using that
hadn't.
today.
I'm not using that today because it was having all kinds of drama. But the other issue is, if you look right there,
You're not using that one today either.
you're really not using that one today. Yes, there. Oh,
Get tech help. Or get Miss Whitaker.
Is that the internet?
what that? No, it looks like it's setting up the computer. It must have had an update or something because it said, "Hi,
How
we're
long
getting
has
things
it been
ready."
since you used it?
I used it yesterday.
Oh.
Yeah, there's no reason it should be doing that.
It's acting like
Don't worry, y'all. It's almost there.
It's acting like it hasn't seen you since before.
Yes.
I know. I don't know. Okay, so I am going to show you this using the computer, okay? But again, One Way ANOVA, you can use a calculator. So when you do your homework problems, you're welcome to just use a calculator, or you can use a computer. You'll see I left spaces for the assignment if you use Excel, okay? All right. So if you read this, it says the temperature at which a manufacturing plant is maintained is believed to affect the rate of production in the plant. Data collected is displayed in the table below. Do these data suggest that temperature has a significant effect on the production level at a 0.05 level of significance? Okay? So these are samples from a plant that is at 68 Fahrenheit. I said point. It's a degree symbol. Good grief. 68 degrees, okay? So you'll see 10, 12, 10, and 9. The next sample is from a plant that is 72 degrees, 7, 6, 7, 8, 7. And then the third sample is from a plant that is 76 degrees. So because our samples are independent, okay, you'll see you don't have to have the same sample sizes. That was true when you had 2 groups first semester, so that's not new. Typically, we try to get about the same sample size just because you don't want to cause people to question it, you know. So if you had 5 from this group and 20 from that group and 12 from that group, they might be like, can you really compare 5 to the 20? You know what I mean? So try to get the same sample size, but it's okay if they're not exactly the same, okay? All right, so if you watch, I'm going to type these in Excel over here. It's on this screen. Everybody watch over here. So I'll show you on this one when you don't include the labels versus on the next one I will include the labels just so you can see what that looks like, okay? And don't worry, I'll zoom it in and make it really big so you can see. Okay? If it will get its life together, which it is not. So, okay, there we go. All right, so that first group, I'm not going to put any labels this time. So you see it had 10, 12, 10, and 9. Okay? Next group had 7, 6, 7, 8, 7. And the last group had 3, 3, 5, 4. 3, 3, 5, 4. Okay? So remember first semester I showed you how to get that extra button when you click the data tab? Everybody remember that? Once you turn this on, it'll always be there. So you click the data tab, which is across the top right there. Then you go over here to data analysis. And when you do that, you'll see we use the histogram first semester to be able to compare the two data sets to one another. Do you remember that? Okay. So on this one, we're not going to do that. We don't need the descriptive statistics. We're going to scroll this up, and you'll see it says ANOVA single factor. That's one way. That's what we're doing. Then you'll also see it says ANOVA two-factor with replication and two-factor without replication. And I'll show you what that means in a later lesson. Okay? So I'm going to click single factor and click OK. And then it's asking me, what's the input range? So I'm going to click this first cell, this top left, drag over for all the lists, and then down. Okay? And it's okay that they don't have the same sizes. The computer can handle that. All right? And then you'll notice I made sure it said columns because I did put my groups in columns. If you had put your data from side to side, you would select rows. I don't ever do it that way. But if you wanted to, just make sure you change that to rows right there. Okay? And then, are there labels in the first row? No, I didn't put any labels on this one. Okay? So I'm not going to select that. Alpha is 0.05, and then yes, I'm just going to let it make a new worksheet. Okay? So I'm going to click OK. And you're going to see it makes a new sheet down here at the bottom. So I'm going to highlight the whole thing, just make it a little bit bigger so I can read it. And you'll see some really important things here. Let me make this bigger again. Whoop. Everybody can see that? Okay. So group one was what? This says column 1. So if I look at my data, that was my sample from 68 degrees, right? So I can change that to say 68 degrees. Okay. Then column 2 was 72 degrees, right? And column 3 was 76 degrees. Okay. And if you look, it says there were 4 samples. They have a sum of 41, which gives you an average of 10.25. And then it says the variance is 1.58. We don't actually look at the variance. We want to compare the standard deviation, okay? So first semester, I really emphasize what is the relationship between variance and standard deviation. What do you do to variance to get standard deviation? Square root it. Good job. So I'm going to type for myself right here, standard deviation. And then I'm going to put in equals, which is on my keyboard. Okay, it's right beside the backspace. Equals SQRT parenthesis. And you'll see that pops up a formula that says square root number. Okay? And then I'm going to click variance, that variance right there, that 1.5833, and hit enter. Okay? Once you've done it in this cell, everybody watch, once you do it in this cell, when you hover over that cell in the bottom right corner, it makes a plus sign. Just drag that down, and if you click on it, it'll show you it's square rooting E6, which is the next variance. And then if you click that one, it's showing you E7. So when you drag that down, it'll use that same command, but the one to the left of it. Does that make sense? Okay, so let's record these. I also like to highlight the averages just so that my brain sees those, okay? Because ANOVA is comparing the averages and the standard deviations, right? So these averages, when you compare them to one another, that's called between groups. So this number right there is going to be representing the difference in these averages. Everybody see that MS? That means mean squares. So how far apart are they? Okay. And then this one is the difference within groups. So if you notice, everybody watch this. It's really cool. When I first taught ANOVA, we did these by hand. It took forever. because you have to compare them all to each other and stuff, and then find the square and add it all. It was crazy. But if you watch, this is my test statistic. What did I tell you the numerator was? It was the difference between the means, right? So if you look, this number right here is 42.25. I'm going to put equals. Let me go down here. Equals, and I'm going to click that number. That's the difference between. So that's the difference of the means. And then divided by the difference between the standard deviations, which is called within groups. Okay? If I click that number and hit enter, look at what you get. You get the test statistic. So that's what the computer is doing for you. It's taking the mean squares between groups divided by the mean squares within groups and giving you that test statistic. You're not going to have to do it by hand, but I'm just trying to explain to you, what are these numbers? Why are they being reported out? Okay? You have degrees of freedom for the numerator and denominator, and then you also have your p-value right there, and then a critical value as well. All right? So remember, that is not standard notation. When you have e to the -5, that's a really tiny number, so we will write it in our note sheet. All right? Everybody good? Okay. All right, back over here so I can write all this with you. So, what were the means for each sample? X bar for the first group was 10.25. X bar for the second group, 7, and the last group, 3.75. Okay, y'all. Look at those averages. Do they look similar? No. These are not very close to each other. So I'm thinking, if I'm talking about my descriptive statistics, this makes me think that I'm going to reject the null that the groups are equal. Okay? So I'm thinking, yes, the temperature in the plant is going to have an impact on the production rates. Okay? And then remember, the Excel gives you variance. So to get this, you have to square root. Okay? Which was equal SQRT parenthesis, and then you just click on the variance and hit enter. Okay? That was a command that I did over there on the desktop. All right? So what were they? 1.26, 0.71, and 0.96. So those standard deviations look similar. Okay? And then your ANOVA report out, degrees of freedom was 2 and 10. I showed you that the numerator, so to find F, was 42.25 divided by this within groups, which was 0.95, and that's why we get 44.47368. And then for the p-value, the computer says 1.05434 E -5. Okay? So remember, what does that mean? Let me write it over here. That means 1.05 times 10 to the -5. Right? You learned that last year in chemistry. It's called scientific notation. So that means you have to move that decimal to the right or left, y'all? Left. Yes, it's a tiny number. So we're going to move this decimal. Oh no, why did it do that? It moved this decimal 1, 2, 3, 4, 5. So if you move it 5 times, that's going to put 1, 2, 3, 4 zeros in front of it. So right here for my p-value, I'm going to put 0.1234 and then 105. Okay? Questions on that? All right. So for these, we always set up our null and alternate, our conditions, right? Okay. So for this one, I'm going to say that the null is at the average for the 68 degree group is equal to the average for the 72 degree group, which is equal to the average of the 76 degree group. Okay? And then the alternate is that at least one of them is different, but we're going to put that they are not equal. Okay? And I don't think they're equal, just from looking at those sample means. I don't think they're going to be equal. Okay? Then we have to check our conditions. So the first condition, just like first semester from you, it was random. Second condition, normal, which if you have a sample of 30 or more, you're good, right? Because of the central limit theorem. It says that the sample will be normal and the population will be normal. If you don't, you have to check the probability plot. Everybody remember that from first semester? You check the probability plot in your calculator. It's the last option to the far right, and you make sure that it's approximately linear. All right, third one, independent. And then the fourth one that you only have to check one time is that the variances are similar. So I am going to answer that one because that data is right up there for me. I'm going to say yes, all close together, because I had 1.26, 0.71, and 0.96. I think those are all close together. Okay? You don't have to give me the calculator instructions since we did this on Excel, but I do want you to tell me what type of test this is. So this is a One Way ANOVA. That's also known as single factor ANOVA. And what is my test statistic? My test statistic was about 44.47. Is that a big number or a small number? Bigger. It's bigger than a ratio of 1, right? So remember, big number means big difference between the means. All right? So this large test statistic indicates that the variance between groups is large compared to the variance within. Also, this large value suggests that at least one group average production rate is significantly different. Okay? All right, so p-value now. I'm going to go over here where I have more room. P-value. That was 0.000105. If the average production rates are equal, Which one is that first part of the sentence? The null or the alternate? The null. So if the null is true, if the production rates, the averages are equal, okay? If the average production rates are equal, then there is a 0% chance that I found that at least one average is different. That's my alternate. Everybody see that? So there's a 0% chance, because even if I move this twice this way, you're going to have 0.001%. That's tiny. So we just put basically 0. There's a 0% chance that I found that at least one average is different by random chance alone. Okay, and now I'm going to compare it to alpha. Good job. 0.1234105 compared to alpha 0.05. That P is low, less than low. So we're going to reject. Okay. So if we reject,
there is official evidence.
There is, yes. There is significant evidence at the 0.05 level of significance to conclude that at least one group average is different. So we rejected. Isn't that what we thought was going to happen when we looked at the sample means? Mm-hmm. And I will tell you, first semester, very last concept you learned, or last chapter rather, when you rejected, when it was chi-squared goodness of fit, do you remember when you rejected? You had to tell me which one was the most different. It was called contributions. Do you remember that? So next class, I'll show you if you reject, okay? And you don't have to write this. I'm just going to write it down. Next class, we will find which one or ones is, well, I want to erase. There we go. Which one is or which ones are different. Okay, it's called a post hoc test. And we use what's called a Tukey's, not turkey. I've had kids call it turkey before. It's called Tukey's HSD. Okay, so you only do that though if you get reject. All right, you only do that next test if you get rejected. Same thing first semester when we rejected the null. Then we wrote what was the most different, which one. Remember we looked at the contributions. If we got failed to reject, we moved on because it wasn't significant, right? Same thing with this. Okay. Any questions for me? All right, I'm going to let you try the next one, but I will put it in Excel for you, okay? So that you can just pull this information from Excel and then run the test. All right, everybody? Okay, so a rifle club performed an experiment on a randomly selected group of first-time shooters. The purpose of the experiment was to determine whether shooting accuracy is affected by the method of sighting used. Only the right eye open, only the left eye open, or both eyes open. 15 first-time shooters were selected and divided into 3 groups. Each group experienced the same training and practicing procedures with one exception, the method of sighting that was used. After completing the training, each student was given the same number of rounds and asked to shoot at a target. The scores are listed in the table. At the .05 level of significance, is there sufficient evidence to reject the claim that the three methods of sighting are equally effective? Okay? So if you'll look, I'll type them over here real quick for you. Okay, so I'm going to make a new sheet. And then I'm going to zoom in so y'all can see it. So this time I'm going to put the labels just so you can see what that looks like, okay? What was the first one? Right eye. Right eye. And then the left eye. And then both eyes. Okay? So right eye had what? 12, 10, what's the next one? 18, 12, 14. Is that it? Okay. Left eye? 10,
17,
17, 16, 13. Is that it?
yeah,
Okay. 16,
14,
14,
16,
16,
11,
11,
20,
woo, 20,
and 21.
21. Okay? So, again, up here at the top it says File, Home, Insert, Page Layout, Formula, Data is what I'm going to select. And then on the far right, I'm going to choose Data Analysis, okay? I'm going to choose Single Factor, okay? And then OK. And I'm going to change that input now. And I'm going to highlight right eye, left eye, both eyes, and then drag down, okay? So because I have labels in that first row, I'm going to click that, okay? And then here is here's the information it reports out for you. Okay? All right. So somebody come up here and type out how to get the standard deviation, okay? I'll be right back. Yes, somebody go do it. Be right back. didn't save my writing? What? Nope. None of my notes have my writing on it, y'all. Okay. Well, I'll just write it all again with you. Okay. Okay. So 212 for the degrees of freedom, 11.34 for the mean squares within groups, 1.286974 is your test statistic, and 0.311619. So that's everything you pulled from the Excel sheet, right? And the means and standard deviations. So your null is that the averages for the right eye group is equal to the average for the left eye group, which is equal to the average for both eyes. The alternate is that at least one is different, so not equal to. For the conditions, you check the first three for each of your groups, right? So they have to be random samples, they have to be normal, they have to be independent. And then the fourth one, which is new for ANOVA, is that the variances are similar. Would you say those standard deviations are similar? Yes, super close, right? Yes, they are close. So then your test statistic, you got the F is about 1.287. So is that a big number or a small number? It's small, right? It is bigger than 1, but it's not really big, okay? The last one's 44, exactly.
Is it like big, like consider like out of 100? So like 1 would be small and 100 would be big?
I sometimes, to get an idea, because that one part says if the ratio is larger than 1. Well, this is larger than 1, but it's 1.28. So it's still pretty close to 1. So I sometimes look at the p-value to get an idea. So 0.3 is going to be bigger, so we're going to fail to reject, which means this would have to be small. 1.28 is small. So this small test statistic indicates what?
The variance between groups is small. Oh.
Mm-hmm.
It indicates that.
Yeah, the variance is between.
Right.
Yeah.
Yeah.
Between means comparing the means to one another. Yeah.
Yeah.
So the variance between.
Small.
Mm-hmm.
Oh, I thought I did it wrong.
No, you're right. Is small compared to the denominator. So compared to the variances. Which one's in the denominator? The variances within, okay? Just remember BW. B's in the numerator, W's in the denominator. So between the groups is means, within. Okay. So that also means what? This suggests what? The small value. This small value suggests
That the averages
yep.
for each method of eye-sighting are similar and the differences are likely due to random chance.
Good job. That the averages for methods of sighting are similar and the differences are likely due to random chance. Very nicely done. Okay, p-value. Oh no, I wrote way too big. I'm gonna change colors and write over here to the side.
That was me last semester.
Okay, p-value. Well, I knew better. I'm sorry. Okay, so the p-value is... Y'all, I can't with this thing. It's driving me nuts. I got most of it, but still, you know what I mean?
See, Thomas used to run motor.
I know. All right, so the p-value is 0.3116. Okay, so if the averages are equal, there is a 31.16% chance that I found that at least one group average is different. Okay? So now let's compare our p-value to our alpha. 0.3116 compared to 0.05 is greater than. So if the p is high, let it fly, right? So fail to reject the null, which means there is or is not.
It's not.
Is not. If you get fail, there's not, okay? So there is not sufficient evidence at the 0.05 level of significance to conclude your alternate. So to conclude that at least one group average is different. Okay? Questions? Any questions? No? Okay. Okay. I'm writing back what it deleted. Okay.